Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. A rectangular solid has length, width, and height of L, W, and H centimeters, respectively. Okay. In my pause there, I'm just reminding myself that this is not necessarily a cube. It would only be a cube if L, W, and H are equal to one another. If these dimensions are increased by X%, Y%, and Z% respectively, so there I pause again and think to myself, it looks like each of the dimensions of this rectangular solid is increasing by a different percent. I don't know for sure that X, Y, and Z are all different, but if they are, then we're getting different different multiplicative changes, different change factors for each of these dimensions. They're each getting multiplied by a different thing. And they want to know what is the percentage increase in the total surface area of the solid. So let's think about this together. What if the change factor was the same for each dimension? What if so for example, think of some rectangular solid, and let's say that I double the length, I double the width, and I double the height. So I'm multiplying every dimension by the same factor. How would that impact the surface area, the total surface area? Would we know? Aditya is using his intuition here and saying, well, it stands to reason that if I double each of the dimensions of this rectangular solid, then also the total surface area would double as well. It would match.
Yeah.
What are some other reactions to that? Because we're going from a one-dimensional measurement, and I know that it's one of the ways to know that we're dealing with one dimension is the units. We're talking about centimeters. But we're going from a one-dimensional thing to a two-dimensional thing, namely area, so that would be measured in centimeters squared. Whatever change factor you apply on the one-dimensional measurements will get squared when it translates into the two-dimensional type of measurement. And if we were talking about the volume of the shape, which is a three-dimensional measurement, then it would be cubed. So, and here's an example, a simplified example. Here we just have a rectangle, just a regular rectangle, 10 by 5. The surface area, since it's a two-dimensional shape, it would just be the area, but imagine surface area. This would be 50. But if I double the 10 and I double the 5, what happens to the area? It doesn't double. It would get multiplied by 2 squared. Why squared? Because we're going from one-dimensional measurements, 10 and 5, to a two-dimensional measurement, area. So the logic there is, since we're going from centimeters to centimeters squared, any kind of multiplicative change is also squared when we go from a one-dimensional to two-dimensional measurement. And again, if it was going from one-dimensional to three-dimensional, it would get cubed. So just to illustrate that, if a large cube has a side length that is 5 times the side length of a small cube, then the volume of the large cube is blank as many times as the volume of the small cube. Can you fill in the blank? 125 times as much. That's right. And I think this is counterintuitive for most of us. This is surprising. So many years ago, I wrote a blog post back when I was working for Manhattan Prep about Dr. Evil and Mini-Me from the Austin Powers movie. But that's all the stuff that's going on in my mind as I'm reading this question. I'm thinking, if x equals y equals z, then I would say that the surface area is getting multiplied by that same change factor squared. A statement that told me, so imagine if statement 2 said, x equals y equals z equals 5. That would be sufficient on its own, because the change factor would be 105 over 100, and we would square that. So whatever that is squared, that's the change factor for the surface area. The total surface area is changing by this factor. And then if we want it as a percent change, how do we find the percent change once we have a change factor? We multiply the change factor by 100 and subtract back out the 100. So this would be the percent change. If it was problem solving, then that's what you would do. But for data sufficiency, you would just say, yeah, that's sufficient. If it said x equals y equals z equals 5. In reality, it's not saying that. It's saying that each of the dimensions is getting multiplied by a different factor. So that on its own can't possibly be sufficient because I don't know anything about what those dimensions are. And that eliminates answer choices B and D. Statement 2 on its own is not sufficient. There's no particular reason why I started with statement 2. I just started with it because we were already talking about it. Statement 1, it still doesn't give me the actual dimensions, but it does give me the ratio of the dimensions. So for example, I can say now that the length is longer than the width, and the height is somewhere in between. We know what the ratio is, but I don't know if we're talking about a shape for which we would need a microscope because it's super tiny, right? This rectangular solid, just based on statement 1 on its own, could be microscopic, or maybe I need a telescope to see it because it's the size of a star in the galaxy. I have no idea how big of a shape we're looking at. So statement 1 is probably the easier statement to evaluate. It doesn't stand a chance of being sufficient on its own. So this becomes a question of C versus E. Right? What happens if I combine these statements? Then am I able to tell the factor by which the total surface area is going to change? So how do I think about that? Well, I know the ratio of these elements, the length, the width, and the height. And I also know the change factor associated with each of them. If this were a two-dimensional shape, would it be sufficient if I combine them? Let's think about that. So let's say that we're talking about this rectangle. And let's say that I know that the ratio is 5 to 3. So let me change these. We'll call it 5x and 3x. That's the length and width. And then I tell you that I increase this one by, well, let's just make it simple, right? We'll double the length and I triple the width. What would happen to the area? Let's see if in a two-dimensional situation it would be sufficient. Yes, the area would be impacted by each of them. So I can say very quickly without any algebra, for the first reason, let's do some color coding here. For the pink reason, the area will double. And separately, for the green reason, the area will triple. So what happens to something if it doubles and also it triples? It gets multiplied by a factor of 6. Because it got both a factor of 2 and a factor of 3. I think what a lot of people would do is they would do some algebra there. They'd say the area is 15x squared, and if I double the length, that's 10x. I triple the width, that's 9x. 10x times 9x, that's 90x squared. Going from 15x squared to 90x squared, that's changing by a factor of 6. But we can sidestep all of that by understanding change factors in a multiplicative story. This is a multiplicative story because length times width equals area. Okay, and by the way, what about a completely different question, say finance? If I double my principal investment and triple the simple annual interest rate and quadruple the number of years, let's just call it the duration of the investment, what will happen to my earned interest at the maturity of this investment? Right, so we're going from a geometry question to a finance question, but the underlying concept, the principle is the same. In both cases, we're talking about a multiplicative story, In the first case, area of a rectangle is the product of length and width. In the second case, and the interest that you earn from an investment is the product of the principal investment multiplied by the number of years that you're investing it in, multiplied by the simple annual interest rate. It's a multiplicative story. What would happen to your interest? Well, again, I can do some color coding here. For the green reason, it's going to double. For the light blue reason, it's going to triple. And for the red reason, it's going to quadruple. So overall, what happens to it? It's getting multiplied by factors 2, 3, and 4, also known as 24. If the question asked what's going to be the percent increase of the volume of this rectangular solid, statement 2 is sufficient on its own. The correct answer would be B in that case, exactly for the reason that JD stated. And that would be exactly analogous to the question that I just created here at the bottom. This question about earned interest would be exactly analogous to the original GMAT question if it was asking if this said volume. If this said volume, it would be exactly analogous, because volume of a rectangular solid is the product of length times width times height, just as earned interest is the product of principal investment multiplied by simple annual interest rate multiplied by number of years. So it would be completely analogous, and for that reason, you're absolutely right, JD. If that word in that big blue rectangle, if that said volume, yes, the answer would be B. Surface area of a three-dimensional shape is a bit tricky because it's not a straight-up multiplicative story. Area of a two-dimensional shape, I should say a two-dimensional rectangle specifically, depending on the shape, but if it was a rectangle, it's a straight-up multiplicative story. The area of a rectangle is simply the product of length times width. Done. Surface area of a rectangular solid, well, that's a bit more tricky, because how do we compute the surface area of a rectangular solid? We're not just multiplying something times something times something. What are we doing instead? We take the product of length times width plus the product of length times height plus the product of width times height, and then we double the sum. But the key words in what I just said were the words plus. I said plus twice. I said length times width plus length times height plus width times height. And the pluses make it such that this is not a multiplicative story. It's a bit more complicated than that. It's actually a sum of three different products. And that's why statement 2 is not sufficient on its own, because it's not a straight up multiplicative story. If it were, meaning if this word said volume, then the correct answer would be B. It's true that the order doesn't matter when you're adding things, but if you're applying different scale factor or different change factors to things that you're adding up, I mean, let's take a much simpler scenario just to wrap our heads around this. If I say that, let's think about something additive. So what would be something additive? Yesterday, I drank 3 cups of water, and today I drank 5 cups of water. Therefore, altogether, I drank 8 cups of water. So a very simple story. Okay? Now, if I ask you the following question, what if I had drank, I'm not sure about the grammar here, but let's go with it. What if I had drank twice as many cups yesterday and thrice as many cups today? What would happen, right? By what factor did my overall drinking volume over the 2 days change? How would we answer that? We'd have to go, okay, 3 times 2 is 6, 5 times 3 is 15, and 6 plus 15 is 21. So I went from a total of 8 cups of water to a total of 21 cups of water. That means that we have a change factor of 21/8. The total volume of water that I drank from day 1 to day 2, from the total volume of water I drank over the 2 days would have been multiplied by 21/8 if I had drank twice as much yesterday and thrice as much today. But we can't get that answer without knowing exactly what the numbers were here and here. We needed those numbers. Without them, we can't solve this. So if I replace the 3 and 5 with x and y, then I'm no longer able to answer this question, because I would just get 2x plus 5y for my hypothetical case, and I don't know what change factor, like how do you go from, algebraically what you'd have in that case is 2x plus 3y divided by, this would be the change factor. And what kind of answer is that in data sufficiency? That means I can't answer, not sufficient. Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below. And give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. Yesterday, I drank 5 times as much water as I did today. What if I drank twice as much water yesterday and 20 times as much water today? What would happen to the overall amount that I drank? So we could say, well, yesterday I drank 5x and today I drank x. But if I had done twice as much yesterday and 20 times as much today, I would have this. So going from 6x to 30x, can we tell the change factor? We can. It's 5 times as much. If we know the ratio of the things that we're adding, and we know the change factor that each of them is getting, we can tell what's happening overall to the sum. It's getting multiplied by a factor of 5. Five x, 3x, and 4x. What would be the surface area? It would be 30x squared. I took 2 times length times width, plus, now I'll do length times height, so 40x squared, plus, and lastly we'd have 24x squared. That's the 2 times width times height. And we want to know what would happen to this if each of these gets a different change factor. So just to make it easier with the change factors, let's imagine that the length is doubled, the width is tripled, and the height gets multiplied by a factor of 5. So how would this affect things? So for the length times width, we would get a factor of 6. That part of the surface area would get doubled for one reason and tripled for the other reason, so overall a factor of 6. So I'm going to call that 180x squared. For the second one, we're getting a factor of 10, so that would be 400x squared. And for the last one, we'd get a factor of 15. So 15 times 24, that's like 5 times 72, which is like 10 times 36, so 360. That was a long way around, but got there. Okay. And then we can say the total here is 94x squared. The total here is, well, whatever it is, we can tell. Since this data sufficiency doesn't really matter. But just for fun, that would be 940, I believe, x squared. Can we tell the change factor? Yeah, it got multiplied by a factor of 10. And I guess the simplified version of that is what we saw here. This is a simplified version where we have an additive story, but we know the ratio of the elements in that additive story to one another. Where was the ratio in the elements? It was here. That's a ratio. So we're given the ratio between the elements in the additive story. And then we're given the change factors for each of them. And we can find the overall change factor of the sum. Now, if you're wondering how is it possible to solve this original question in under 2 minutes, probably my best answer is if you imagine using a scale factor for statement 1. So if you imagine that these are 5x, 3x, and 4x, and then think about multiplying each of those by a known change factor. We don't really care what specifically the change factor is because it's data sufficiency. The point is we know what the change factor is for each of these elements. Then when we add them up, we'll be able to take the x out as a common factor, or in this case, the x squared out as a common factor when we add up the elements. And since the question is only asking for a ratio, that common factor that we took out is going to get reduced. How do I know they're asking for a ratio? Because look, this is going to be a ratio. A percent is by definition a ratio. So percent increase, we prefer to think of that as a change factor. And what's the definition of a change factor? New over original. That's the factor by which something has changed. It's a ratio. And in a ratio, if you have the same common factor in the top and in the bottom, it's going to end up getting reduced. And that's exactly what happened to us here. We had x squared, which we pulled out as a common factor. Let me highlight that as well for you. So we had this common factor in our additive story. Same here. When we look at the ratio of those things, the common factor, the x squared, gets reduced. So if you can play the movie forward without having to write all of this down on paper, if you can just in your mind play forward what it would end up looking like when you apply some kind of scale factor, unknown scale factor here, 5x, 3x, 4x, and then imagine multiplying each of them by the appropriate change factors, and then realize that's just going to reduce at the end. Therefore, yes, it is sufficient when we combine them, and the answer is C. It's an additive reasoning question disguised as a multiplicative story, because if just changing one thing would have made it multiplicative, just this word. Changing it to volume would have changed the answer, because it would be a multiplicative story rather than an additive story. But it's not a number line question. It's a change factor / scale factor question, right? It's a very complicated ratio question in the context of an additive story. The key is the fact that we have the ratio of those elements, though. Imagine that we're talking about the perimeter of a rectangle. That would be completely analogous. The perimeter of some rectangle, what would happen to it if I know that the rectangle is such that the length is 3 times as long as the width? So we know that, and we want to know by what factor would the perimeter change? Again, perimeter is a additive kind of element, right? It comes from adding together the length and width twice. So by what factor would the perimeter change if we were to double the length and triple the width? Right? That would be the analogous question, just removing one dimension from the whole thing to make it a bit simpler to wrap our heads around. And what we would say is, well, the length would become 6x, the width would become 3x. So instead of a parameter of 8x, that's the original parameter, instead of 8x, we'd have 18x, if I didn't make any mistakes. Can we tell the factor by which the perimeter has changed? Yes. It's getting multiplied by 9/4, or if you prefer percent change, it would be increasing by 125%. The reminder how we go from change factor to percent change is we multiply 100 times the change factor and then multiply back out that 100 to get the percent change, which in this case would be 125%. My hope is that we didn't just learn how to solve this question, but rather we used this question to deepen our conceptual understanding of the concepts that are tested in this question. So we're looking at it from a much higher level, in a much more general sense. That's always our goal here. It's not about the question itself, it's what can we use this question for to further our reasoning in general, which again will hopefully push our score up on the GMAT. My other hope is that we won't need to memorize this takeaway from a flashcard because we get it on a much deeper level because we discovered it ourselves. So that's another one of my hopes for these sessions. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.